you how to perform a two-way analysis of variance or two-way ANOVA in SPSS. You'll want to run a two-way ANOVA if you have a single continuous dependent variable, so something measured with numbers, and you have two independent variables. And you'll bias yourself toward the ANOVA over regression if you have categorical variables and you're not so concerned about between group differences. You really just want to talk about main effects and interaction effects of those two variables. So let's start off by going to the class website. Let's get over here. Okay, great. We're in week 3 now, and we're running on our two-way ANOVA video right now. What I have for you is our SPSS checklist, so I'll open that up. What we care about here, not really the general considerations or anything. I'm going to scroll on down to the next page. I'm going to run through the two-way analysis of variance here, and I have some notes to kind of help guide you along with the video. I suggest modifying these notes to fit your needs. I'm going to use the plant growth 2 data set as it says right here. We can find that. Let me get rid of this under our practice data sets here. So if we click on this, it'll be the first data set we come to, and let's inspect this a little bit. We've got a fertilizer condition. There's fertilizer X, fertilizer Y, so that's one of my independent variables. Notice, categorical. And I have watering. I'm either doing it once or twice for each fertilizer. And then we have our dependent variable, the height of the plant, and that's measured on some kind of continuous scale. Let's assume it's inches or something along those lines. Okay, so I need to get this into SPSS. So as usual, I'll just highlight my data, copy, and we'll jump on over to SPSS. That didn't help me. Okay, great. So I just need to go to variable view now, give us some names. So our fertilizer is the first one, our watering schedule is the second one, and then we have our height. These are correctly identified as string and numeric. The measures would be nominal for the first two, scale for the third one, and I feel pretty good about this. Head back to the data viewer, make sure everything looks just about right. And now I'm ready to run my two-way ANOVA. So we'll make sure none of these values look weird. We'll go into graphs and box plot. So I just want to put up a quick plot of these, make sure there's no outliers. With only 20 data points, I can see there aren't any outliers, but let's do a clustered box plot here. And my variable of interest is height. Now it doesn't matter which independent variable you put on the x-axis or define as the clusters. This just kind of depends on your experimental design. It really doesn't matter either way. I'm going to put the fertilizer on the axis and watering as the cluster. It will make absolutely no difference if you do one or the other. What you're going to see is a plot that looks something like this, where watering twice gives me taller plants regardless of fertilizer, and fertilizer X looks a little taller than fertilizer Y. So looking at the data, I'm expecting that I'm going to have an effect of fertilizer and an effect of watering. Not expecting an interaction, but we'll see what we get here. Looking up top, I can see that I have an equal number of cases in each of these groups, so there's 5 plants in each group. This is what we call a balanced design. This is advantageous because it maximizes statistical power. So if you can have a balanced design, that's great. If you have different numbers in each group, it's what we call unbalanced. Just keep in mind you might miss some effects that are there. We can see no cases are missing, so I've got really no problem with my data. So let's jump into it. So back in our data view here, we'll go Analyze, and now General Linear Model, Univariate. So now I add my dependent variable of height to dependent variable. Unlike last week, I now have more than one fixed factor, so I'll go ahead and highlight both of these and add them in. At this point, I want to now add some plots. I want to add an interaction plot. So I'm going to take one of those independent variables, put it on the horizontal axis, and make separate lines for the other independent variable. Again, does not matter which one you use. You should just think about what makes the most sense for how it's going to be organized, and that depends on the type of variables you have. This makes sense to me, so I'm using it. And I'll click Add, and notice I've got one independent variable, an asterisk there, and then the other independent variable. That's telling me it's an interaction plot. I'm going to include some error bars here. That's going to help me make better sense of the plot. And I'll click Continue. For post hoc test, we needed these last week when we ran our analysis of variance because we had more than 2 groups. We don't this time. Fertilizer is either X or Y, and watering is either once or twice. So I don't need to run any post hoc tests here. I do need my estimated marginal means. That's the EM means. We can get it for everything. I really don't care about everything. But I want to add it for fertilizer, watering, and the interaction. And here I want compare main effects. There's no reason to adjust, but as a habit, I want to get in the habit of selecting Bonferroni just in case I have more than 2 groups. I don't here, but that's fine. We'll click Continue there. And I do want to save the unstandardized residuals. And this is going to allow me to make some plots and make sure I'm not violating some of the assumptions of the analysis of variance. Under options, it's nice to have some descriptive statistics. Those will just let me take a look at the averages in my data set. I don't actually care about estimates of effect size, but I will include them because some folks do. Partial eta squared doesn't mean much to me, but we're all snowflakes. I'm going to include homogeneity tests because this is an important assumption of the analysis of variance. So this will give us a Levene's test that we can take a look at. And I'm going to say I'm fine here. We'll click OK. And finally, we get our output. We got our descriptive statistics. This will let me take a look. Hey, look at that. I'm getting like a 4.8 point increase with watering more. With X fertilizer, with fertilizer Y, it's 4.4 inch increase, so pretty similar. All right, so this backs up the plots that I looked at earlier. Don't care much about that. I'm looking here at the Levene's test. Here, I'm not seeing anything going on, so homogeneity of, equal variance is assumed here. Homogeneity of variance, same thing. Before I dive too deeply into the effects here, I want to check some assumptions here. I want to look for the normality of my residuals. That's why I saved the residuals over here. So before I jump in here, I need to come back to my data window, and we're going to go to Analyze, Descriptive Statistics, and Explore. Just like last week. Rather than adding height, what I'm going to do is add the residuals. And my independent variables then to the factor list. I want, under plots, I don't care about stem and leaf. I want histogram. And I would like normality plots with those tests. And at that point, I'm all good. At this point, I can click OK. This will drop some more stuff down here. I don't really care about the descriptives. I'm going to jump down to tests of normality. So across my different fertilizers here, what am I seeing? Nothing going on. Neither of these normality tests is indicating that I have an issue. If I look at my histograms, I know it doesn't look like a bell, but it looks close enough to a bell, I suppose. Looking at our QQ plot, couple of things we can get from this. I'm following the line pretty well. I'm not deviating too far off the line. I don't see any trend to me that would suggest that this line isn't a good description. So I have homoscedasticity. That's maybe a little easier to see in these detrended QQ plots. for fertilizer X, fertilizer Y. Yeah, maybe you could try to draw a line here, but you'd be missing this point and that point. No, the straight line actually looks pretty good here. And my box plots look fairly symmetric. We'll do the same exercise for watering. No reason to think that I've got a difference between my watering groups. Again, I know the histograms don't look awesome, not a bell curve, but we're not dealing with that many data points. Let the statistics guide you up here. Neither test is telling me that I have a p-value less than 0.05, so we're going to move on. We'll again look at our QQ plots. We're following the line. This is great. We can look at them detrended. Exact same thing we saw above. In this case, the flat line is the best fit here, so I'm not too worried. It sort of looks like maybe a positive trend if we forget a couple of data points. Taking them all into account, everything looks pretty good. So we think we have good normality of residuals based on our, for example, Shapiro-Wilk test up here. And we have our homogeneity of variance by looking at the Levine's test earlier and then examining these QQ plots. So we're following those lines pretty well. I feel like we can run with our analysis of variance, and hell, I would anyway. That way we know how to walk through the data. But we haven't violated any assumptions, so great. All right, we go to our tests of between subjects effects. This is the table we want to take a look at. I don't really care much about this top row here. This is just the overall model. I don't really care about the intercept. What I'm looking at is fertilizer and watering. So these two rows are telling me about the main effect of fertilizer. Do I have one? Yes, absolutely. We look at the p-value here, certainly less than 0.05. How about watering? Same thing. So there's a main effect of fertilizer, main effect of watering. Do I have an interaction effect? Absolutely not. And what that tells me is that the effect of watering does not depend on which fertilizer I got. Water is still good for plants. And the effect of fertilizer didn't depend on how much water the plant was getting. We can look at our adjusted R squared. That tells us how much difference in plant height we're kind of accounting for with just these two variables alone, and it's pretty good. Certainly more than half of the variance. That's fine. We don't really care because we're not trying to predict plant height from these two variables alone or anything. We just want to see if the two variables make a difference at all. Below that, we want to then inspect our main effects. So we do have main effects. How big of an effect is it? Well, comparing fertilizer X to fertilizer Y, here are their estimated marginal means. We don't care about the confidence interval. So here we have about a 3.6 point difference between them. That's shown here. This is telling me that X minus Y gives me a positive value, so X is bigger than Y. We see that up here. Now, is this difference statistically significant? Well, yes, we saw a main effect of fertilizer in this table above, and when we look at our p-value, certainly less than 0.05, and we look at our confidence interval. 0 is not included. Now, what's a meaningful difference in plant height? I don't know. If we say it's 3 inches or something like that, sure, we might have a meaningful difference in plant height. I don't know what that value is, but we want to have some idea of how big of an effect really matters. Is my confidence interval telling me that I should believe that that effect is true? We can do the same exercise for watering. We saw a main effect of watering above. When we do our pairwise comparison, plant height of watering compared to twice, we're getting this negative value here, positive below. These are the same comparison, we're just switching the order. Watering once gives you smaller plants. Watering twice gives you bigger plants. How much bigger? Somewhere between about 2.7 and 6.5, let's say, inches. So watering seems to have a much bigger effect than the type of fertilizer used, but if you want to maximize your plants, from this we should conclude that we want to use fertilizer X and water twice. Now let's look at the interaction. This is just giving me the means. It's not showing me group differences or anything like that. We want to look at this plot here. Now, we didn't have a significant interaction above. Looking at our interaction plot, what I want you to notice is the slope of these two lines are the same. Sure, watering twice is higher than watering once for both fertilizer X and fertilizer Y. And when we compare the difference between these, it's the same. In other words, the effect of watering is consistent between the two types of fertilizers used. Now, if we had an interaction effect, then these two lines would have different slopes. And we'd have to do some follow-up here. So what do we want to report then? Well, some people like to report partial eta squareds. They don't mean a lot to me. How do I translate this to inches? I can't. I'd have to know a whole lot more information. So sure, some people have a habit of reporting partial eta squareds, but what I want you to think about reporting would be confidence intervals for differences. How big of an effect did fertilizer X have? 1.7 to 5.5 inches. How much does it improve whenever you water twice? 2.7 to 6.5 inches. That means a whole lot more than telling someone if you water twice, your partial eta squared will be 0.623. Awesome. What does that mean, right? That's not going to mean anything to a farmer or someone who has house plants that they want a little bit taller. So when you're thinking about what to report, it's really confidence intervals for differences that matter. Now, if you need to get out some nerdy stuff like some F statistics, degrees of freedom, absolutely that's given here in the table, and you should spit those out at people so that they have them at their fingertips. You should report p-values, but you absolutely want to pull out these confidence intervals. And in my SPSS checklist, I give an example of what kinds of stuff you might want to report. All right, that's it for this video. Make sure you check out the others this week so we can learn how to handle some other ways of analyzing multiple independent variables. If you have any questions, make sure you make use of the questions box. Hope to hear from you later.